Hi friends, today we'll discuss about the equivalence of non-deterministic finite state machine and deterministic finite state machine. To prove that Ndfsm and DFSM are equivalent to each other, we have to prove first, for every DFSM there is an equivalent Ndfsm. So we can prove it by let M be a DFSM that accepts some language L. M is also a Ndfsm that happens to contain no epsilon transitions and whose transition relation happens to be a function. So, the Ndfsm that we claim must exist is simply M. Similarly, we have to prove that for each Ndfsm, there is an equivalent DFSM. This can be proved by construction. Given a Ndfsm, M is equals to K summation delta SA, we construct M dash is equals to K dash summation delta dash S dash A dash, where K dash contains one state for each element of P of K. S dash, that is the new start state, is equals to EPS of old start state S. EPS also called as Epsilon Closure of old start state S. A dash, that is the new accepting states, are Q, which is a subset of K, where Q intersection A is not equal to null, and delta dash of Q comma A is equals to union of EPS of P, where P belongs to K and QAP belongs to delta for some Q belongs to Q. This is the algorithm which computes M dash deterministic finite state machine given non-deterministic finite state machine M. Ndfsm to DFSM given a non-deterministic finite state machine M. In the first step, for each state Q in K, we are supposed to compute EPS of Q or epsilon closure of each state. So before discussing this algorithm further, let us see what actually you mean by computing EPS. As we know, epsilon transition is a transition that allows movement from one state to another without consuming a character of input string. If an Ndfsm has epsilon transitions, then we must first handle them by calculating the epsilon closure, that is EPS for each state. The epsilon closure EPS of Q is the set of states acceptable from state Q by epsilons, that is EPS of Q is equals to P, which belongs to K, where Q comma W for multiple instances derive P comma W. Let us see the algorithm used to calculate the EPS. Given a state Q to the EPS, by default Q is in the result. Next, if P belongs to result and R does not belongs to result and there is a transition from P to R with epsilon in delta, then insert R into the result and return the result. It means connect all the states that can be reached on epsilon. For example, I have P and a transition from P to R with epsilon. And if I want to find out the EPS of P is equals to, so initially from this step By default, P is in the result. Next, P is in the result, R is not in the result, and there is a transition from P to R with epsilon, then insert R into the result. So from P to R with epsilon transition, so R is in the result. Similarly, R is in the result and I have a transition from R to T with epsilon. Then T is also included in the result. Therefore, all the states which are reachable from P on epsilon are P, R and T. Let us see some examples of calculating the EPS for the given Ndfsm. Given this Ndfsm, we are supposed to find out the EPS of Q0, Q1, Q2 and Q3. So first, according to the algorithm, EPS of Q0, by default Q0 is included in the result. Next, Q0 being in the result, check is there any epsilon transition going from Q0 to any other state. So we can see here from Q0 there is a transition to Q1 with epsilon. Then Q1 is also included in the result. Next, from Q1 do we have any epsilon transition? Yes, it is going to state Q2. So Q2 is included in the result. Next, from Q2 do we have any epsilon transition? Yes, going to state Q0, but Q0 already is in the result, so no need to include it. Next, do we have any transition to Q3? No, we don't have any epsilon transition to Q3. So the final result, that is EPS of Q0, is Q0, Q1, Q2. Next, similarly, check for EPS of Q1. So according to the algorithm, Q1 is by default in the result. Then from Q1 epsilon transition, it is going to state Q2. So Q2 is included in the result. From Q2 an epsilon transition is going to state Q0. So Q0 is included in the result. Whereas from Q3 we don't have any epsilon transitions. So this is the final result or EPS for Q1. Next, EPS of Q2. So by default Q2, then from Q2 epsilon transition is going to Q0. So Q0 is included in the result. Again from Q0 epsilon transition is going to Q1. So Q1 is in the result, whereas there are no epsilon transitions from Q3. So this is the final EPS. Coming to EPS of Q3, by default Q3, and there are no other epsilon transitions from Q3. So this is the final result or EPS of Q3. So this is how we are supposed to calculate the EPS for all the states. Let us see one more example of calculating EPS. Given Ndfsm, we are supposed to calculate EPS of Q0, Q1 and Q2. First, EPS of Q0. By default, Q0 is in the result. Q0 is in the result, and from Q0 there is an epsilon transition going to state Q1, then Q1 is also included in the result. Next, from Q1 again there is a epsilon transition going to state Q2. So Q2 is also included in the EPS. So EPS of Q0 is Q0, Q1, Q2. Next, coming to Q1, by default Q1 is in the list. Then from Q1 there is an epsilon transition going to state Q2, so Q2 is included, but there is no transition for Q0. So the final result EPS of Q1 is Q1, Q2. Coming to Q2, so by default Q2 is in the result. Then from Q2 there is no transition going to state Q0 or Q1 with epsilon. Hence the result is Q2. So EPS of Q2 is equals to Q2. Let us apply this Ndfsm to DFSM algorithm on an given Ndfsm to obtain its equivalent DFSM. Let us apply this Ndfsm to DFSM algorithm on a given Ndfsm to obtain its equivalent DFSM. First step is to compute the EPS for each state in the machine. Given this Ndfsm, just now we have obtained EPS for all the three states. EPS of Q0 is Q0, Q1, Q2. EPS of Q1 is Q1, Q2, and EPS of Q2 is Q2. So once we obtain the epsilon closure for all the states, next step is to obtain the new start state of the DFSM. So new start state of DFSM S dash is equals to EPS of old start state, that is start state of Ndfsm. So the start state of Ndfsm in this particular machine is Q0. So EPS of Q0 is equals to Q0, Q1, Q2. Hence the new start state of DFSM is equals to Q0, Q1, Q2. And at present the machine looks like initial state, which is Q0, Q1, Q2, and at present we have only one active state of the DFSM. Here summation is 0, 1, 2. In step 3, we compute delta dash of active state Q0, Q1, Q2. That is Q0, Q1, Q2, 0, 1 and 2. So let us compute one by one. Q0, Q1, Q2, 0 is equals to EPS of delta of Q0, 0 union delta of Q1, 0 union delta of Q2, 0. That equals to EPS of Q0, 0. So Q0, 0 is taking a self loop going to Q0. Q1, 0, Q1, 0, there is no transition. Q2, 0 also there is no transition. So we are left with EPS of Q0. EPS of Q0 is Q0, Q1, Q2. So Q0, Q1, Q2, 0 goes to Q0, Q1, Q2. Similarly, for Q0, Q1, Q2, 1 is equals to EPS of delta of Q0, 1 union delta of Q1, 1 union delta of Q2, 1. That is equals to EPS of Q0, 1, we don't have any transition. Q1, 1 self loop Q1. Q2, 1, again we don't have any transition. So EPS of Q1 is equals to Q1, Q2. Therefore Q0, Q1, Q2, 1 is going to state Q1, Q2. Last, EPS of delta of Q0, 2 union delta of Q1, 2 union delta of Q2, comma 2. This is equals to EPS of Q0 2, there is no transition. Q1 2 also there is no transition. Q2 2 is having a self loop to Q2. Therefore, EPS of Q2 is just Q2. So Q0, Q1, Q2, 2 is going to state 2. So by now you can see here Q0, Q1, Q2, 0 is going to state Q0, Q1, Q2. 1 is going to Q1, Q2 and 2 is going to Q2. So we have obtained 3 active states by this step. That is, from the start state Q0, Q1, Q2, 0 is going to the same state taking a self loop. 1 is going to a new state, that is Q0, Q1, and 2 is going to state Q2. So as of now we have obtained 3 active states Q0, Q1, Q2, Q1, Q2 and Q2. So next step is to obtain the delta transitions for the other 2 active states Q1, Q2 and Q2. So let's start computing the delta transitions for the active states Q1, Q2 and Q2. First, Q1, Q2, 0 is equals to EPS of delta of Q1, 0 union delta of Q2, 0. That is equals to EPS of Q1, 0, there is no transition. Q2, 0, also there is no transition. So EPS of null is equals to null state. Next, Q1, Q2, 1 is equals to EPS of delta of Q1, 1 union delta of Q2, 1. That is equals to EPS of Q1, 1 is having a self loop to itself. So Q1, Q2, 1, there is no transition. EPS of Q1 is equals to Q1, Q2. So Q1, Q2 is for 0 it is going to null state. Q1, Q2 for 1 it is going to Q1, Q2. Next, Q1, Q2, 2 is equals to EPS of delta of Q1, 2 union delta of Q2, 2. This is equals to EPS of Q1, 2, we don't have any transition. Q2, 2, a self loop. So EPS of Q2 is just Q2. So Q1, Q2, 2 is going to Q2. Similarly, Q2, 0. Q2, 0 is EPS of delta of Q2, 0. We don't have any transition, so it is equal to null. Next, Q2, 1 is EPS of delta of Q2, 1. Again Q2, 1 we don't have any transition, so it is null. Last, Q2, 2 is equals to EPS of delta of Q2, 2. That is equals to EPS of Q2, which is nothing but Q2. So Q2, 2 is going to state Q2. So once we obtain the delta transitions for all the states, so the DFSM obtained as of now is Q1, Q2, 0 is going to a null state, which is also called as a dead state or a trap state, which may be or may not be represented. So at present I am not representing the null state. Q1, Q2, 1 a self loop. Q1, Q2, 2 a transition to state Q2. Q2, 0, Q2, 1 again going to null state, and last Q2, 2 going to state Q2, that is self loop again. So step 3 will be continued until no new states are active. At present, active states did not change. So the delta has been computed for each element of active state. Finally, for the given Ndfsm, the DFSM obtained is this, where the states are Q0, Q1, Q2, Q1, Q2 and Q2, and the accepting states are, in Ndfsm the accepting state is Q2. In DFSM, wherever we have Q2, all the states will be accepting. Hence, all the three states Q0, Q1, Q2, Q1, Q2 and Q2 will be accepting or final states. So this is how we convert given a NDFSM to its equivalent DFSM by using NDFSM to DFSM algorithm. This is our second NDFSM, which is to be converted into DFSM. So the first step is to compute the EPS of all the states present in the given NDFSM. So let us compute the EPS of all the states. EPS of Q0. By default, Q0 is in the list. From Q0, we have an epsilon transition going to state Q1. So Q1 is in the EPS of Q0. Q1 is in the EPS of Q0, and from Q1 there is an epsilon transition going to state Q3. Then Q3 is also included in the EPS of Q0. No other epsilon transitions. So EPS of Q0 is Q0, Q1, Q3. Next, EPS of Q1. So by default, Q1 is in the list, and from Q1 we have an epsilon transition going to Q3. So Q3 is also included in the EPS of Q1. Coming to Q2. Q2 in the list, and from Q2 we don't have any epsilon transitions. Hence EPS of Q2 is Q2. Q3. By default Q3, and from Q3 also we don't have any epsilon transition. So EPS of Q3 is Q3. Coming to EPS of Q4. So Q4 in the list, and from Q4 we have two epsilon transitions, one going to Q2, another going to Q5. So Q2, Q4, Q5 is the EPS of Q4. Last, Q5. EPS of Q5 is Q5 only, because no other epsilon transitions present in it. So this is how to obtain the EPS of all the states in the given NDFSM. Actually, Q0 is in the In step 3, compute the delta transitions for the only active state Q0, Q1, Q3. That is Q0, Q1, Q3 0 and Q0, Q1, Q3 1 is equals to EPS of delta of Q0, 0 union delta of Q1, 0 union delta of Q3, 0. This is equals to EPS of delta of Q0, 0. Q0, 0, there is no transition. Next, Q1, 0. So Q1, 0 is going to state Q2, and Q3, 0. So Q3, 0, you can see here, it goes to state Q4. So EPS of Q2 and Q4. Q2 is Q2, Q4 is Q2, Q4, Q5. So union of these two will be Q2, Q4, Q5. So Q0, Q1, Q3 for 0 is going to state Q2, Q4, Q5. Similarly, we have to calculate for 1. EPS of delta of Q0, 1 union delta of Q1, 1 union delta of Q3, 1. This is equals to EPS of delta of Q0, 1. So Q0, 1 is going to two states. One is Q0, the other one is Q3. Q0, Q3. Then Q1, 1. Q1, 1, we don't have any transitions. Q3, 1. Q3, 1. Again, we don't have any transitions. So EPS of Q0, Q3. Q0 is Q0, Q1, Q3 and Q3 is Q3. So union of these two will get Q0, Q1, Q3. Therefore, Q0, Q1, Q3 for 1 is going to Q0, Q1, Q3. So once the delta transitions are computed for the state Q0, Q1, Q3, Q0, Q1, Q3 0 is going to a new state Q2, Q4, Q5 and 1 is going into a self loop. So by now we came across two active states Q0, Q1, Q3 and Q2, Q4, Q5. So next step is to compute the delta transitions of the new active state Q2, Q4, Q5. Q2, Q4, Q5 0 is equals to EPS of delta of Q2, 0 union delta of Q4, 0 union delta of Q5, 0. That is equals to EPS of delta of Q2, 0. Q2, 0 we don't have any transitions. Q4, 0. So Q4, 0 also we don't have any transition. Q5, 0. So Q5, 0 is going to Q4. So EPS of Q4 is equals to Q2, Q4, Q5. That is Q2, Q4, Q5 for 0 is taking a self loop. Similarly, EPS of delta of Q2, 1 union delta of Q4, 1 union delta of Q5, 1 is equals to EPS of delta of Q2, 1. So Q2, 1 is going to state Q5. Q4, 1. Q4, 1 is going to Q1 and Q5, 1. So Q5, 1 we don't have any transition. So EPS of Q1 and Q5, Q1 and Q5, union of these two is Q1, Q1, Q3 and Q5. So therefore Q2, Q4, Q5 for 1 is going to state Q1, Q3, Q5. So in the DFSM, Q2, Q4, Q5 for 0 is going into a self loop and for a 1 it is going to the state Q1, Q3, Q5. As of now, the active states are Q0, Q1, Q3, Q2, Q4, Q5 and Q1, Q3, Q5. Next, we are supposed to compute the delta transitions for the active state Q1, Q3, Q5. So let's compute Q1, Q3, Q5 for 0 and 1. For 0 is equal to EPS of q delta of q1 comma 0 union delta of q3 comma 0 union delta of q5 comma 0, that is equals to EPS of q1 0. q1 0 is going to state q2, q3 0 is going to state q4, and q5 0 is going to state q4. So EPS of q2 and q4 is equals to q2, q4, q5. So q1, q3, q5 0 goes to q2, q4, q5. Similarly, for 1, EPS of delta of q1 comma 1 union delta of q3 comma 1 union delta of q5 comma 1, that is equals to EPS of q1 1. q1 1 we don't have any transition, q3 1 also we don't have any transition, q5 1 also we don't have any transition. This is equal to null. So q1, q3, q5 for 1 is going to null state. So after computing the delta transitions for q1, q3, q5, q1, q3, q5 0 is going to q2, q4, q5, and for 1 it is going to a null state. So the active states are q0, q1, q3, q2, q4, q5, q1, q3, q5, and null. And by now the active states did not change, and the delta has been computed for each element of the active state. So from the given Ndfsm, this is the DFSM obtained with the states q0, q1, q3, q2, q4, q5, q1, q3, q5, and null state, and wherein q0, q1, q3 is the initial state. Coming to the accepting state, in the Ndfsm, q2, q4, and q5 are the accepting states. So in DFSM, wherever you have q2 or q4 or q5 states, all the states will be accepting. So here we don't have any q2, q4, q5 state, so this is intermediate state. Coming to this state, all the three states are available in this state, so this state is an accepting state. Coming to this state, here q5 is present, and since q5 is an accepting state, this state also will be an accepting state. So in this DFSM we have two accepting states, q2, q4, q5, and q1, q3, q5. So this is the final DFSM obtained from the given Ndfsm. Let us see one more example of converting a given Ndfsm to its equivalent DFSM. The first step is to compute the EPS of all the states present in the Ndfsm, and the EPS obtained for q0 is q0 q1, q1 is q1, q2 is q2, q3 is q0 q1 q3, q4 is q4, and q5 is q5. Once we obtained the EPS, next step is to find the new start state of the DFSM S dash, which is equals to EPS of the start state of the Ndfsm. So EPS of q0 is equals to q0 q1. So the new start state of DFSM is q0 q1. So the next step is to compute the delta transitions for the only active state q0 q1. So q0 q1a goes to q2 q4, q0 q1b goes to q0 q1 q3. That is, from q0 q1 a goes to a new active state q2 q4, and b also goes to a new active state q0 q1 q3. So as of now we have three active states, q0 q1, q1 q2 q4, and q0 q1 q3. So next step is to compute the delta transitions for the active states q2 q4 and q0 q1 q3. After computing the delta transitions for the states Q0, Q1, Q3 and Q2, Q4, we obtain Q0, Q1, Q3A going to state Q2, Q4, B a self loop. Similarly, Q2, Q4 for A going to a new state Q1, Q2, Q4, and for B going to another new state Q0, Q1, Q3, Q5. So totally as of now we come across 5 active states, and next step is to compute the delta transitions for the new active states generated Q1, Q2, Q4 and Q0, Q1, Q3, Q5. After computing the delta transitions, Q1, Q2, Q4 takes a self loop for A. For B, it is going to state Q0, Q1, Q3, Q5. Similarly, from Q0, Q1, Q3, Q5, A is going to state Q2, Q4 and B is going to state Q0, Q1, Q3. Now we can see that all the active states have their delta transitions and there is no change in the active states. So given a Ndfsm of 6 states, the DFSM obtained consists of 5 states, among which, coming to the accepting states, in Ndfsm Q2 and Q5 are accepting. So in DFSM, wherever we have state Q2 or Q5 or both, all those states will be accepting, rest all will be rejecting. Hence here Q2, Q4, Q1, Q2, Q4, Q0, Q1, Q3, Q5. So these 3 states will be accepting, whereas the other 2 states will be rejecting states. So this is how by using Ndfsm to DFSM algorithm we can convert a given Ndfsm to DFSM. Thank you.